15 minutes. We'll hope you finish.
Okay.
We'll do a question.
Sounds great. All right, so today I'm going to be talking about some small illuminated peaks that we were finding at the poles of the moon. Just to give you a little bit of background in case you're not familiar, the Earth is tilted at 23.5 degrees, which is why we get seasons. Meanwhile, the moon is only tilted at 1.5 degrees, and so there's some regions at both the North and South Pole that remain in persistent shadow, and there's some other areas that are also right nearby that remained illuminated for a majority of the year. Right now on board the LRO spacecraft are two imaging systems. One is the wide-angle camera, which provides 100-meter per pixel images of the moon. And so far we've collected, we're approaching 7,000 images of both the North and South Pole. In addition to the wide-angle camera, there's also two narrow-angle cameras. These have a much narrower field of view with a 5.7 degree combined field of view, and they provide meter scale images of the polar regions. And right now we're approaching and surpassing about 4,000 images for both the North and South Pole. With those two imaging systems, we're able to make some high resolution polar mosaics. On the left-hand side, you'll see the wide-angle camera polar mosaic for the South Pole, and this map is at 100 meters per pixel. There's a little blue insert there, and that is the NAC mosaic you see on the right. The NAC mosaic that we have, which we've released as part of the March 15th RDR release, is a 2 meter per pixel map of the polar region, going from about 85.5 degrees to the pole. And we have one for both the North and South Pole. And just to give you an idea of what these images look like, there's a small little blue box right around here. And if we go to the next slide, you can kind of see what it looks like at higher resolution. And so right here is the edge of Shackleton, and then we just have some illuminated terrain there. And inside that small little blue box, we can kind of see what we're able to see at almost full resolution here. So this gives you an idea of what we're able to acquire with the two camera systems. So with the wide-angle camera, we acquire an image about every 2 hours of the pole in our 50-kilometer orbit. The average time between our observations is about 2.2 hours. This includes instrument upset spacecraft, other spacecraft operations where we have to turn off the instrument for pass over the poles. And each time we go over, we basically start acquiring an image at 80 degrees, and we go all the way over the pole and then back over to 80 degrees on the other side. And these images can be arranged in movie sequences to show how the lighting conditions change over time. And so the next few slides kind of highlight what you can kind of see. So instead of showing a movie, I was kind of afraid that it would mess up somehow, so I'd rather not show a movie. So instead I'm going to show a couple individual frames. And so this right here is Perry Crater and Whipple Crater located right next to the North Pole. And this is with subsolar latitude being about 1.5 degrees. Subsolar longitude in all these images is about 150 degrees. So we're getting the sun coming from the same direction. We're just changing the subsolar latitude so you can see how it changes over time. So in this case, we're at plus 1.5. Then we go down 0.5. Now we're at minus 3. And then minus 1.5. So you can see how just, even though we're only tilted at 1.5 degrees, throughout the year, the lighting conditions change drastically over time. And we'll reverse the sequence so you can kind of see how more regions become illuminated as the sun gets a little bit higher. And so yeah, you can see what we're able to see with our movie sequences. These same movie sequences can also be used to make multi-temporal illumination maps. Basically what we do is we have all these map projected images, and we can convert each one of those frames into binary images. Basically one being illuminated, 0 being not illuminated. And we can stack those up and look at each map pixel and calculate how long each map pixel is illuminated for. And you can see on the right-hand side, on the top is the North Pole illumination map, and on the bottom is the South Pole illumination map, and you can see how long different regions are illuminated for. And we are seeing a slight disconnect between currently published illumination models, which have been made with topography, and the reason for that is we're a little bit higher resolution than their studies have previously done. So that can explain one of the disconnects, because basically what we're doing is, so when they were looking at topography information, their pixels that they were using were much larger, and so when we're using smaller pixels, this 100 meter by 100 meter pixel might not be illuminated, but the one next to it is. And so that's why our percentages are a tad lower, but you can kind of see our two products. But the regions that remain illuminated for a long period of time are still remaining illuminated for a long period of time in our analysis. So, and another thing we can do is test previous models using both the WAC and the NAC. The NAC has a relatively small field of view, and so we don't have a lot of multi-temporal coverage, but what we can do is spot check previous topography models. And so we have identified some regions that are illuminated in times when we thought they weren't supposed to be illuminated, and we've also found other cases where regions were in shadow when we thought they were to be illuminated. This area is called Point B. It's supposed to be illuminated for about 82% of the year. We found cases here where the images show that region is not illuminated, but there are regions nearby that remain illuminated during that time. And in addition, that same region is supposed to be in shadow for about a 10-day period, and right in the middle of that 10-day period, there's this small illuminated peak that we're able to image that we see illuminated during that time. And so that's kind of cool. So instead of having this 10 days of darkness, we have 5 days of darkness, a little bit of sun, and then probably another 5 days of darkness. And the two cameras on board the spacecraft are going to continue targeting these regions throughout the rest of the mission, and we'll have a great data set for future explorers. In addition to, we've also been comparing our images, our NAC images, to LOLA simulations. So on the left-hand side, you'll see a LOLA simulation made with their 240 meter per pixel DEM. On the right-hand side, you'll see a NAC image of the same terrain taken at the same time. We've also found, just in comparing those models, we've also found some other small illuminated peaks. There's 3 examples here. Some of these, we found some that are just 3-4 pixels wide, but they kind of make really boring images for PowerPoint presentations. But here you can see a couple of the larger ones that we've seen. And as I said before, we're still going to continue to target these areas that are supposed to be in shadow to see if we can find any of these small illuminated peaks. These regions of extended illumination are great for future human and robotic explorers, and 2 reasons for that is because of their benign thermal environment and near continuous access to solar energy. One way to extend the period of time that you're illuminated is by building tall towers and to kind of go over some of these areas that will put you into shadow. Another way to extend the amount of time is surface mobility. So if you're going all the way to the moon and you're setting up a base or exploring the polar regions, you're probably going to have some amount of mobility. And so what we're looking at is looking for these small regions where if you could travel in a 2.25 kilometer area, you can remain illuminated for a majority of the time. So instead of building a 10 meter tall tower, or 20 meter or 30 meter tall tower, if you're able to move 500 meters in each direction, okay, that extends the amount of time you're illuminated to like 90%. So that's one thing that we're looking at. In addition to just looking at direct illumination, we can also look at indirect illumination, illuminated sources. Here we have a NAC image where it's being lit kind of from right here, and the sun is bouncing off the edge of this crater and bouncing back into the shadowed region. And if you're really close, and hopefully the people in the back can see on the high-def TVs, that you can also see some small little craters that are actually doubly shadowed, so they're not receiving any direct or indirect sources of illumination. And this could be helpful if you're looking for polar volatiles or cold traps or anything like that. So this is a great resource, and you can find it in a lot of our images. But you have to look at images where the geometry is right, where you have the sun coming in, bouncing off a crater rim, and bouncing back in. It's not going to be, you can't just do this to any region at the poles. You have to, it has to be under the right lighting conditions. So in summary, the WAC and NAC cameras have been imaging the poles at a very high frame rate over the last several years, and will continue to do so throughout the rest of the mission. And they're able to provide images at much higher spatial resolutions than other satellites and instruments have been able to provide us. We've been able to see some small illuminated peaks that are just tens of meters wide, and help, and this can be used to help locate resources as well by looking at areas of permanent shadow and doubly shadowed regions. And so this will be a great data set for future human and robotic explorers as they go back to the moon. So, thank you.
Any questions?
One of the interesting features I picked off of one of your maps.
Mm-hmm.
Russell Cox, Reflection Engineering. One of the interesting features I picked off of one of your maps is there's near point B, there's also another little hill. And those are locations where you have, like within a 5-kilometer distance, places that are essentially permanently shadowed next to places that are essentially in sun, so that in a relatively short traverse, you could cover a lot of different soil possibilities.
Right, there are several key locations, that being one of them, and there's other locations around each of the poles that are in areas of extended illumination, which will help for explorers, and they're really close to places in shadow where we can find these resources. So.
What is the availability of these images for use in other applications?
Great question. So all the movie frames are available online. They were released on March 15th. That covers, I believe, February 15th of 2010 to February 15th, 2011. All the other images, 3 months old, are basically on the PDS, and you can download them there. We also have all the maps are already uploaded as part of our RDR releases. So.
Spacecraft spice kernels?
Those, I believe, are available through NAIF. Yeah.
Any other questions? I actually have one. Is there an evolution of the illumination pattern over years, or is it repeatable, highly repeatable, so that in 2030 the same illumination pattern could be expected for a launch as you're seeing today?
Well, there is an 18-year cycle, and so this pattern will be repeatable in 18 years. So it is important that we continue throughout the mission. We'll get some other data sets that will be able to, other images that will be able to help us and get a better handle on what areas are exposed to illumination for longer periods of time. So,
Okay,
but it is fairly repeatable.
Okay.
So.
Is that everything? Okay. Thank the speaker.